In 2003, the philosopher Nick Bostrom, then at Yale University, published a paper titled, "Are You Living in a Computer Simulation?" It was not a work of science fiction. It was a serious philosophical argument based on probability, and Bostrom proposed that one of three things must be true. One, civilizations like ours almost always go extinct before they can develop the technology to run realistic simulations of their ancestors. Two, advanced civilizations for some reason lose all interest in running such simulations. Or, three, we are almost certainly living inside one. He formalized this simulation argument, and it carried a disturbing implication. If our reality is a program running on some advanced computer, our creators could alter the laws of physics at will. They could change a constant, delete a particle, or simply turn off our reality at any moment. This idea of flawed or incomplete physical laws is not just for philosophers. It is the single biggest problem in fundamental physics today. We have two great theories of the universe. One is general relativity, Albert Einstein's theory from 1915. It describes the big things: gravity, planets, stars, galaxies, the curvature of space-time. It works perfectly on its own scale. The other is quantum mechanics, developed in the 1920s by a host of physicists like Bohr, Heisenberg, and Schrödinger. It describes the small things: atoms, electrons, photons, the probabilistic nature of reality. It also works perfectly on its own scale. The problem is, they do not work together. When you try to use them in the same place, the math breaks down. It produces nonsense, infinities, contradictions. These breakdowns happen in the most extreme places in the universe, inside a black hole. At the moment of the Big Bang, these are the places where the very large meets the very small. Gravity is so strong that it affects individual particles. Space-time is so curved that quantum effects matter. And in these places, our two best descriptions of reality give us two different, incompatible answers. It is as if our own universe has a glitch in its source code. These are not just mathematical curiosities. They are profound paradoxes that challenge our understanding of space, time, information, and existence itself. Number 15, the black hole information paradox. A black hole is not actually black. It glows with a faint thermal radiation. Stephen Hawking calculated this in 1974. This glow, called Hawking radiation, means a black hole will eventually evaporate and disappear. And this process seems to destroy information, which violates one of the most fundamental laws of quantum physics. Here is the conflict. General relativity gives us a simple picture of a black hole. It is a region of space-time where gravity is so strong that nothing, not even light, can escape. According to a theorem from the 1970s called the no-hair theorem, a black hole is incredibly simple. Completely with just three numbers: its mass, its electric charge, and its angular momentum. Any object that falls into a black hole contributes its properties to these three totals. A book, a planet, a star, it does not matter. All the complex information that made up that object, the arrangement of atoms in the book, the chemical composition of the star, is seemingly lost forever behind the event horizon. The black hole has no hair, no other features to record what it ate. Now bring in quantum mechanics. A core principle of quantum theory is called unitarity. It means that information about a physical system can never be permanently destroyed. It can be scrambled, hidden, or rearranged, but it is always preserved. If you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any other time, past or future. Burning a book seems to destroy its information, but it does not. The information is just transformed into the energy and smoke and ash encoded in the quantum states of all those particles. It is hard to read, but it is still there. In 1974, Stephen Hawking combined quantum field theory with the curved spacetime of a black hole. He discovered that the intense gravity near the event horizon creates pairs of virtual particles. Sometimes one particle falls into the black hole and the other escapes. To an outside observer, it looks like the black hole is emitting particles. This is Hawking radiation. Hawking's calculation showed this radiation is thermal. It is completely random, like the glow from a hot piece of charcoal. Its temperature depends only on the black hole's mass, not on what fell in. This is the paradox. The black hole slowly radiates away its mass. Over an immense amount of time, it will evaporate completely. When it is gone, what is left is just this bath of random thermal radiation. The information that fell into the black hole is not in the radiation because the radiation is random. The information is not left behind in some remnant because the black hole is gone. So where did the information go? General relativity's black hole swallowed it. Quantum mechanics, through Hawking radiation, seems to have erased it from the universe. This violates unitarity. Physicists have wrestled with this for nearly 50 years. In 1997, a famous bet was made between Stephen Hawking and John Preskill, a Caltech physicist. Hawking and his colleague Kip Thorne bet that information was truly lost. Preskill bet it was not. In 2004, Hawking publicly conceded the bet. He had come to believe that subtle quantum correlations in the outgoing radiation might preserve the information after all, though the exact mechanism was still a mystery. But conceding the bet did not solve the problem. It just deepened the question. How does the information get out? General relativity says nothing can escape the event horizon. To get the information out, you seem to need a new kind of physics, a theory of quantum gravity. The paradox remains a central battleground where our two best theories of the universe fight to a standstill. Number 14, the Firewall Paradox. You are falling towards a black hole. General relativity says your journey across the event horizon should be uneventful. For a large enough black hole, the tidal forces would be so weak you would not even notice the moment you pass the point of no return. This is Einstein's equivalence principle. Freefall is indistinguishable from being in empty space. But in 2012, a group of physicists proposed a new and terrifying idea. They argued that to save quantum mechanics from the information paradox, the event horizon must be a wall of fire that instantly incinerates anything that touches it. This idea, called the Firewall Paradox, emerged from a deeper look at the information problem. Let us accept that information must escape the black hole. This is the consensus view among most quantum physicists. The information must be carried by the Hawking radiation. For this to happen, each particle of Hawking radiation that leaves the black hole must be quantum mechanically entangled with the particle that fell in. Entanglement is a deep quantum connection. Two entangled particles are part of a single system, even when separated by vast distances. Measuring one instantly affects the other. So, an outgoing Hawking particle, let's call it B, must be entangled with its partner particle that fell into the black hole, let's call it A. This is how the information about what fell in gets encoded into what comes out. But there is another problem. Like, the process that creates Hawking radiation requires that the outgoing particle B must also be entangled with all the other Hawking radiation that has already left the black hole, let's call that C. This leads to a contradiction based on a quantum rule called the monogamy of entanglement. A quantum system can only be fully entangled with one other system at a time. It cannot be fully entangled with two separate systems simultaneously. So the outgoing particle B cannot be fully entangled with both its infalling partner A and the previously emitted radiation C. You have to choose. The paradox was laid out in a 2012 paper by physicists Ahmed Almheri, Donald Maringoff, Joseph Polchinski, and James Sully. They showed that if you uphold two fundamental principles, the equivalence principle from general relativity, nothing special happens at the horizon, and unitarity from quantum mechanics information is not lost. You run into this entanglement contradiction. Something has to give. They proposed a radical solution. They suggested that the equivalence principle is what breaks. When you reach the event horizon, the entanglement between the infalling and outgoing particles is instantly broken. The energy released by this violent severing of quantum bonds would create a firewall, a high-energy region that would destroy any infalling observer. This creates a new paradox. You have two completely different descriptions of reality depending on who you are. The observer falling in sees a wall of fire. The observer far away sees nothing unusual at the horizon, just a source of faint thermal radiation. General relativity is built on the idea that physical laws are the same for all observers. The firewall proposal shatters this. The firewall paradox forces a choice between cherished principles. Do we abandon Einstein's equivalence principle, the smooth, gentle nature of space-time at the horizon? Or do we abandon unitarity, the foundation of quantum information, or is there a third option that we have not yet discovered? Some physicists propose that space-time itself is not fundamental but emerges from entanglement, a concept called ER equals EPR. This idea from Juan Maldacena and Leonard Susskind suggests that a wormhole and Einstein-Rosen bridge, or ER, is equivalent to a pair of entangled particles, an Einstein-Podolsky-Rosen pair, or EPR. Perhaps this geometric connection resolves the entanglement monogamy problem, but this too is highly speculative. The firewall paradox shows that even trying to solve one problem at the intersection of GR and QM can create a new, even more bizarre one. Number 13, the problem of singularities. At the center of every black hole, and at the very beginning of the universe, general relativity predicts a point of infinite density and infinite space-time curvature. This point is called a singularity. But a singularity is not a physical object, it is a mathematical error message. It is the point where the equations of general relativity break down and cease to make sense. In the 1960s, Roger Penrose and Stephen Hawking proved a series of singularity theorems. These theorems showed that under very general conditions, singularities are an unavoidable feature of general relativity. If you have enough matter in one place to form a black hole, a singularity is inevitable. If you run the expansion of the universe backward in time, you inevitably hit the Big Bang singularity. Einstein himself was deeply troubled by this. He thought it was a flaw in his theory and that some new physics would prevent these infinities from forming. From the perspective of quantum mechanics, infinities are a sign that a theory is incomplete, and quantum theory smooths out the world at small scales. The uncertainty principle states that you can never know both the precise position and momentum of a particle. This fundamental fuzziness prevents particles from collapsing to an infinitely small point. Your gravity, as described by general relativity, has no such fuzziness. It just keeps crushing matter smaller and smaller without limit. So what really happens at the center of a black hole? General relativity says it is a point of infinite density. Quantum mechanics says that idea is absurd. Reality should be finite and well-behaved at all scales. The expectation is that a theory of quantum gravity would resolve the singularity. Instead of an infinite point, we might find a Planck star, an incredibly dense but finite object held up by quantum pressure. Or perhaps space-time itself dissolves into something else, a network of quantum loops or a vibration of a string. The Big Bang singularity is an even bigger problem. It represents the beginning of time and space in our current model. But if it is an infinity, what does that mean? How can the universe emerge from a point where the laws of physics do not apply? Again, quantum gravity is expected to provide the answer. Theories like loop quantum cosmology suggest the Big Bang was not a beginning, but a big bounce. Our universe could be the result of a previous universe collapsing and then bouncing back out, with quantum gravity effects preventing the formation of a true singularity. The existence of singularities in our best theory of gravity is a huge paradox. It tells us that general relativity is missing a crucial piece of the puzzle. It is like having a map of the world with a giant hole in the middle labeled, "Here be dragons." You know, we know the dragons are not real, we know there is something there, but our map cannot describe it. Quantum mechanics tells us infinities should not exist in the physical world. General relativity insists that they do. Until we can resolve this, we cannot claim to understand the origin of our universe or the ultimate fate of matter inside a black hole. Number 12. The Cosmological Constant Problem. And quantum mechanics predicts that empty space is not empty. It is a bubbling, fizzing sea of virtual particles constantly popping in and out of existence. This activity gives the vacuum a certain amount of energy. When we calculate how much energy the vacuum should have based on quantum field theory, we get a ridiculously large number. It is about 10 to the power of 120 times larger than the energy density we actually observe in the universe. This is the single worst prediction in the history of physics. Let us break this down. In general relativity, energy and mass are sources of gravity. They curve spacetime. An energy of the vacuum, a cosmological constant, would act as a sort of anti-gravity. A positive vacuum energy would cause space-time to expand at an accelerating rate. A negative vacuum energy would cause it to collapse. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery. They found that the expansion of the universe is not slowing down as everyone expected. It is speeding up. There is some kind of dark energy pushing everything apart. This dark energy behaves exactly like a small positive cosmological constant. The value of this observed dark energy is tiny. Here is the paradox. Quantum field theory predicts a huge value for the vacuum energy. It predicts a value so large that if it were real, the universe would have been ripped apart in the first fraction of a second after the Big Bang. Stars and galaxies would never have had a chance to form. But our astronomical observations show a vacuum energy that is not zero, but is about 120 orders of magnitude smaller than the theoretical prediction. This is often called the vacuum catastrophe. Why is the vacuum energy so much smaller than predicted? It is not just a small error. It is like measuring the size of a room and predicting it to be larger than the observable universe. Something is profoundly wrong in our understanding. Physicists have tried to solve this for decades. One idea was that some unknown symmetry in nature might force the vacuum energy to be exactly zero. Perhaps the contributions from all the different quantum fields, electrons, photons, quarks, etc., perfectly cancel each other out. This would be an incredible coincidence, but it seemed more plausible than the 10 raised to the power of 120 discrepancy. But the 1998 discovery of cosmic acceleration showed that the value is not zero. It is small, but it is there. This makes the problem even harder. We now have to explain not only why the vacuum energy is not huge, but also why it has the specific tiny non-zero value that it does. There are many speculative ideas. Maybe some of the assumptions in the quantum field theory calculation are wrong. Maybe gravity works differently at very large scales. Maybe the anthropic principle is the answer. In this view, there could be a multiverse with many different universes, each with a different value for the vacuum energy. We just happen to live in one of the very rare universes where the vacuum energy is small enough to allow for the formation of galaxies and life. This is a deeply unsatisfying explanation for many physicists, as it feels like giving up on finding a fundamental reason. The cosmological constant problem is a direct clash between the quantum description of energy and the relativistic description of gravity. Where quantum theory says empty space should be full of energy, general relativity says that much energy would have a dramatic gravitational effect. Observation says that effect is almost, but not quite, zero. This is arguably the deepest and most embarrassing paradox in modern physics. Number 11. The problem of time. In quantum mechanics, time is absolute. It is a universal clock that ticks away in the background, the same for everyone. It is the T in Schrodinger's equation. It is the stage on which quantum events unfold. But in general relativity, time is relative. It is part of a four-dimensional fabric called spacetime. As gravity can warp time, a clock on the surface of the Earth ticks slower than a clock in orbit. For a person falling into a black hole, time slows to a stop relative to an outside observer. Time is not a background stage. It is a dynamic player in the cosmic drama. This fundamental disagreement about the nature of time is a major obstacle to uniting the two theories. When you try to write down a quantum equation for the entire universe, a problem arises. The equation, known as the Wheeler-DeWitt equation, has no time variable in it. The just disappears. This is the problem of time. The equation seems to describe a static, timeless universe. This is obviously at odds with our experience of a dynamic, evolving cosmos. How can this be? In general relativity, the state of the universe can be described by the geometry of spacetime. But the theory has a feature called background independence. This means the equations do not depend on a pre-existing coordinate system or a fixed background clock. The geometry of spacetime itself is what you are solving for. When you try to apply the rules of quantum mechanics to this background independent theory, the part of the math that would normally represent time evolution just vanishes. So where did time go? There are a few different philosophical and physical approaches to this paradox. One idea is that time is an emergent property. The fundamental reality described by quantum gravity might be timeless. Our perception of a flow of time could be an illusion, a consequence of how we as complex classical systems interact with this timeless quantum reality. It might emerge from things like quantum entanglement, where the correlations between different parts of the universe create a semblance of a sequence of events. Another approach is to try to reformulate one or both of the theories. Some physicists believe that the way we apply quantum mechanics is flawed. Perhaps we need a new formulation of quantum theory that does not rely on a fixed background time. Others believe general relativity needs to be modified. Maybe there is a preferred foliation of spacetime, a special way to slice it up into moments of time that is hidden from us. The problem of time is not just a philosophical debate, it has practical consequences for building a theory of quantum gravity. How do you describe probabilities in a quantum theory if there is no time for things to evolve? The concept of probability in standard quantum mechanics is about the likelihood of a certain outcome at a certain time. Without time, what does probability even mean? This paradox cuts to the heart of our most basic intuitions. We experience life as a sequence of moments, a journey from past to future. Quantum mechanics treats this journey as fundamental. General relativity treats it as a geometric feature that can be bent and stretched. The combined theory seems to get rid of it altogether, reconciling the timeless block universe of relativity with the ticking clock of quantum mechanics is one of the deepest conceptual challenges in physics. Number 10. The measurement problem in a curved spacetime. In quantum mechanics, a particle like an electron does not have a definite position until you measure it. It exists in a superposition of many possible states at once, described by a mathematical object called a wave function. When a measurement is made by an observer, the wave function collapses into a single definite state. This is the infamous measurement problem. What constitutes a measurement? What is an observer? Does it have to be a conscious being or just a piece of lab equipment? Quantum mechanics does not give a clear answer. Now, let's place this problem into the world of general relativity. In GR, the distribution of matter and energy determines the curvature of spacetime. But if a particle's location is not definite until it is measured, what is its effect on spacetime? Does a particle in a superposition of two different locations create a spacetime that is also in a superposition of two different curvatures? This is a profound paradox. Let us say you have a single massive particle in a box. According to quantum mechanics, you can prepare it in a superposition where it is on the left side of the box and the right side of the box at the same time. On the left, its mass would curve spacetime in a certain way. On the right, it would curve spacetime in a different way. If the particle is in a superposition, does spacetime itself go into a superposition? The standard Copenhagen interpretation of quantum mechanics, with its sudden collapse of the wave function, creates a mess. If the collapse is a real, instantaneous physical process, it seems to violate the principles of relativity. An instantaneous change across a spread-out wave function would be faster than light. And who decides when the collapse happens? If two observers are moving relative to each other, they might disagree on the exact moment of the collapse due to the relativity of simultaneity. This disagreement could lead to contradictions about the state of spacetime. One famous thought experiment that highlights this is Schrodinger's cat in a Wigner's friend scenario. It involves multiple observers and nested quantum systems. When you add gravity to the mix, it gets even worse. You can imagine a scenario where a massive object is put into a superposition, and depending on where it collapses, it creates a gravitational field that affects the ticking of a distant clock. The ambiguity of when the collapse occurs leads to an ambiguity in the flow of time itself for a distant observer. Some interpretations of quantum mechanics, like the many worlds interpretation, avoid the collapse postulate. In this view, every measurement causes the universe to split into multiple branches, one for each possible outcome. So the particle on the left and the particle on the right both exist, but in different parallel universes. In this context, space-time would also split. There would be one universe with space-time curved one way, and another universe with it curved the other way. This avoids the paradox of collapse, but at the cost of a vastly multiplied reality that is impossible to verify. The measurement problem is already one of the biggest conceptual headaches in quantum theory. When combined with a dynamic, malleable spacetime from general relativity, it becomes a nightmare. We do not know how to describe the gravitational field of a quantum system that is not in a definite state. This is a fundamental roadblock. It shows that we need a deeper understanding of both measurement and spacetime before we can truly unite them. Number 9, the Unruh effect. As an observer floating in empty space, far from any gravitational fields, will see a perfect vacuum, but an observer who is accelerating through that same empty space will see something completely different. They will feel warm, they will detect a thermal bath of particles surrounding them. This is the Unruh effect, predicted by physicist William Unruh in 1976. The effect is a direct consequence of combining quantum field theory with the idea of an accelerating reference frame, which is a key concept in general relativity. The paradox is simple. What is real? Is space truly empty, or is it filled with particles? The answer seems to depend on who you ask, or more precisely, on how they are moving. The Unruh effect is closely related to Hawking radiation. Both involve the perception of thermal particles in a vacuum due to gravitational or accelerational effects. In Hawking's case, it is the intense gravity at a black hole's event horizon. In Unruh's case, it is uniform acceleration. The mathematics are very similar. The equivalence principle in general relativity states that gravity is locally indistinguishable from acceleration. So, in a sense, an accelerating observer is creating a tiny artificial event horizon behind them. The temperature of this thermal bath, the Unruh temperature, is proportional to the acceleration. To detect a temperature of just 1 Kelvin, you would need to accelerate at about 10 to the power of 20 meters per second squared. This is an enormous acceleration, far beyond anything we can achieve with current technology, which is why the effect has never been directly observed. But it is a firm prediction of our current theories. The paradox deepens when you think about the particles themselves. Where do they come from? For the inertial observer, they do not exist. For the accelerating observer, they are real. They could, in principle, be detected. This challenges our notion of what a particle is. It suggests that the concept of a particle is not fundamental, but is observer-dependent. This has profound implications for a theory of quantum gravity. If two observers cannot even agree on the number of particles present in a region of space, how can they agree on the space-time curvature that those particles create? Does the accelerating observer's detector clicking from detecting an unruh particle cause a tiny change in the gravitational field that the inertial observer who sees no particle cannot account for? It forces us to confront the question of what is truly fundamental in our description of reality. Is it the field, which exists everywhere, or the particles, which are excitations of the field? The Unruh effect suggests the field is more fundamental, and our perception of it as particles is tied to our state of motion. The effect also raises questions about energy conservation. The accelerating observer is detecting particles which have energy. Where does this energy come from? The answer is that it comes from the force that is causing the observer to accelerate. The observer is doing work on the quantum fields around them, and this work manifests as the thermal radiation they detect. The Unruh effect is a stark example of how relativity of motion from GR and the quantum nature of fields from QM combine to produce a result that defies our everyday intuition. The very existence of matter seems to depend on how you are moving. A true theory of quantum gravity must provide a coherent picture in which both the inertial and accelerating observers' perspectives are valid and consistent. Number 8, non-locality versus locality. Quantum entanglement is what Einstein famously called spooky action at a distance. If you have two entangled particles, say A and B, you can separate them by billions of light years. If you then measure a property of particle A, you instantly know the corresponding property of particle B. It seems like a signal has traveled between them faster than the speed of light. This is quantum non-locality. General relativity, on the other hand, is built on the principle of locality. This principle states that an object is only directly influenced by its immediate surroundings. Any influence from a distant object must travel through the intervening space, and it cannot travel faster than light. Gravity, for instance, does not act instantaneously. If the sun were to vanish, the Earth would continue to orbit for about 8 minutes, the time it takes for the change in the gravitational field to propagate to us at the speed of light. This creates a deep tension. Quantum mechanics seems to have a built-in non-locality, while general relativity has a built-in locality. Now, it is important to be precise. You cannot use entanglement to send a message faster than light. The outcome of the measurement on particle A is random. You only see the correlation when you later compare your results with the results from particle B, a process that requires classical communication limited by the speed of light. So there is no violation of causality, but the paradox is more subtle than that. The spooky action is a real feature of how quantum mechanics describes the world. The state of particle B really does seem to depend on a measurement performed on particle A, no matter how far away it is. The two particles are part of a single, indivisible quantum state. How does this non-local quantum reality fit into the local, geometric reality of space-time? The geometry of spacetime in general relativity is what defines the separation between events and enforces the light speed limit. It provides the very framework for what local means. Quantum non-locality seems to operate on a different level, as if it is not constrained by this geometric framework in the same way. The conflict becomes more acute when you consider gravity. What happens if you have an entangled pair of massive particles? If you measure the position of particle A, the wave function collapses. This act of measurement seems to have a non-local effect on particle B, but now the position of particle A also determines its gravitational field. Does the gravitational field also change instantaneously to reflect this new definite position? And what about the gravitational field of particle B, whose state is now also determined? This is a very difficult question. It touches on the measurement problem again. If the gravitational field itself can be in a superposition, then perhaps it can also be entangled. Maybe space-time itself has non-local properties. Some theories of quantum gravity, like string theory, do incorporate non-local effects. The fundamental objects are not points but strings, and their interactions are inherently smeared out, which can lead to a form of non-locality. The paradox of non-locality versus locality is a clash of fundamental worldviews. Is the universe a collection of local interactions propagating through space-time, as relativity suggests? Or is it a deeply interconnected, holistic system where separations in space do not always mean true separation, as quantum mechanics suggests? A successful theory of quantum gravity must reconcile these two pictures. It must explain how the spooky, non-local quantum world gives rise to the familiar, local, classical world of our experience governed by the speed of light. Number 7, the holographic principle. A region of space can only contain a finite amount of information. You might think that the maximum amount of information you can store in a volume depends on the volume itself. If you double the size of a box, you can store more stuff, more information, but when you combine general relativity and quantum mechanics, you get a shocking result. The maximum information content of a region of space does not depend on its volume. It depends on the area of its surface. This is the holographic principle. It was first proposed by Gerard Hooft in 1993, and later given a more precise formulation by Leonard Susskind in 1995. The idea emerged directly from studying the thermodynamics of black holes. Jacob Bekenstein showed in the early 1970s that a black hole has entropy. The entropy is a measure of disorder, but it can also be thought of as a measure of information. The entropy of a black hole, Bekenstein found, is proportional to the area of its event horizon, not its volume. This was a strange and profound result. It was as if all the information about the three-dimensional interior of the black hole was somehow encoded on its two-dimensional surface. The holographic principle generalizes this idea to any region of space-time, not just black holes. It suggests that our three-dimensional reality might be a projection, a hologram of information stored on a distant two-dimensional surface that surrounds us. The fundamental laws of physics might be written on this boundary surface, and the universe we experience is just a holographic image of that code. This sounds like science fiction, but it has a very concrete mathematical realization in string theory. In 1997, Juan Maldacena discovered a powerful duality called the ADS-CFT correspondence. He showed that a theory of gravity in a certain type of five-dimensional spacetime called anti-de Sitter space, or ADS, is mathematically equivalent to a quantum field theory without gravity on the four-dimensional boundary of that space, a conformal field theory, or CFT. This correspondence is a working example of the holographic principle. Everything that happens in the five-dimensional universe with gravity can be described by the four-dimensional quantum theory on its edge, and vice versa. It is like a dictionary that translates between the two descriptions. Difficult problems in gravity can sometimes be solved by translating them into simpler problems in the quantum field theory, and vice versa. The paradox here is about the nature of space itself. We perceive the world as having three spatial dimensions. But if the holographic principle is correct, this might be an illusion. The true reality might have fewer dimensions, and the extra dimension we perceive could be an emergent property of the underlying physics. It also changes our understanding of locality. If the fundamental reality is on a boundary surface, then two points that are close together inside the 3D volume might correspond to points that are far apart on the 2D surface. The way information is organized in the hologram is very different from our everyday intuition. The holographic principle is not a proven law of nature. Our universe is not anti-de Sitter space. It is expanding and has a positive cosmological constant. But the principle is a powerful guide in the search for a theory of quantum gravity. It suggests that space-time is not fundamental. It is an emergent structure that arises from a more basic quantum system with less information than we thought. The conflict between the volume of space, our classical intuition, supported by GR in weak fields, and the surface area, the limit imposed by black hole thermodynamics and quantum information, is a deep clue. It tells us that our understanding of space, dimension, and information is likely to be radically overturned by a final theory. Number 6, the nature of space-time foam. On the large scales of galaxies and stars, space-time is smooth and gently curved, just as Einstein's theory describes. But what does it look like at the smallest possible scales? In 1955, the physicist John Wheeler suggested that if you could zoom in to the Planck length, a fantastically small distance of about 10 to the power of 35 meters, space-time would not be smooth at all. It would be a chaotic, turbulent, bubbling mess. He called this quantum foam, or space-time foam. The idea comes from applying the quantum uncertainty principle to space-time itself. The uncertainty principle can be stated in terms of energy and time. You cannot know the precise energy of a system for a very short interval of time. There are always energy fluctuations. According to general relativity, energy curves space-time. Therefore, these tiny, fleeting energy fluctuations should create tiny, fleeting fluctuations in the curvature of space-time. At the Planck scale, these fluctuations would become so large that the very concepts of smooth space and a linear flow of time would break down. Space-time would be a foam of tiny wormholes, bubbles, and other complex geometries constantly appearing and disappearing. The geometry of space would be probabilistic and uncertain, just like the position of an electron. This creates a paradox. General relativity is a deterministic theory. If you know the geometry of space-time and the distribution of matter and energy at one moment, you can, in principle, calculate its entire past and future. It is a classical non-probabilistic framework. Quantum mechanics, however, is fundamentally probabilistic. The idea of a quantum foam forces us to treat the stage of reality space-time itself as a quantum object, subject to the same rules of probability and uncertainty as the particles that live on it. This is a direct contradiction of the assumptions of both theories. Quantum field theory is typically formulated on a fixed, smooth space-time background. It assumes the stage is stable, but if the stage itself is a roiling foam, how can you even define things like particle propagation or field interactions in a consistent way? Furthermore, a foamy spacetime would have observable consequences. A particle of light, a photon, traveling through this foam would be slightly deflected by the tiny fluctuations. Over billions of light years, these tiny deflections could add up. High-energy photons should be affected more than low-energy photons. This would lead to a blurring of images of distant objects like quasars. However, observations from telescopes like the Fermi Gamma Ray Space Telescope have looked for this effect and have not found it. The images of distant galaxies are much sharper than many models of space-time foam would predict. This does not rule out the idea of space-time foam entirely, but it puts severe constraints on it. Perhaps the foam exists, but its effects are much smaller than originally thought. Or perhaps space-time is fundamentally smooth after all, and our ideas about applying the uncertainty principle to geometry are wrong. The paradox of space-time foam is the paradox of what happens when the stage becomes one of the actors. General relativity describes the stage. Quantum mechanics describes the actors. Quantum gravity requires the stage to obey the rules of the actors. The concept of a quantum foam is a direct, intuitive picture of what that might look like, and it clashes directly with the smooth, continuous picture that both our theories in their current forms rely on. Number 5. The Grandfather Paradox and Quantum Time Travel. General relativity permits the existence of closed time-like curves, CTCs. These are pathways through space-time that loop back on themselves, allowing for travel into the past. Kurt Gödel, a friend of Einstein, found the first such solution in 1949. While Gödel's rotating universe model does not describe our own, other solutions involving wormholes or infinitely long spinning cylinders also allow for CTCs. General relativity does not forbid time travel to the past. This immediately raises the classic grandfather paradox. A time traveler goes back in time and kills their own grandfather before he meets their grandmother. This prevents the time traveler's parent from being born, which means the time traveler themselves is never born. If they are never born, they cannot go back in time to kill their grandfather. This is a logical contradiction. Classical general relativity has no good way to resolve this. One idea is the SL consistency principle proposed by Igor Novikov, and it states that the only solutions to the laws of physics that can occur locally are those which are globally self-consistent. In this view, you simply cannot kill your grandfather. Something would always happen to prevent you. The gun would jam, you would slip on a banana peel, you would have a change of heart. The laws of physics would conspire to ensure no paradoxes are created. This feels unsatisfying and deterministic as it removes free will for the time traveler. Now let us introduce quantum mechanics. The quantum world is probabilistic, not deterministic. This opens up new ways to think about the grandfather paradox. One idea, proposed by David Deutsch in 1991, uses the many-world interpretation of quantum mechanics. When the time traveler goes back in time, they do not travel to the past of their own universe. Instead, their journey on the CTC takes them to a parallel universe. In this new universe, they can kill the person who would have been their grandfather. This has no effect on their own timeline because it happened in a different branch of reality. They have successfully killed their grandfather, but they have also orphaned themselves from their original universe. No paradox is created. Another quantum approach involves the idea of quantum information. If the time traveler is a quantum system, their state is described by a wave function. As they travel along the CTC, they interact with their younger grandfather, who is also a quantum system. The calculations show that the interaction tends to favor outcomes that are not paradoxical. Instead of having a 100% chance of killing the grandfather, or a 0% chance, the quantum probabilities adjust themselves to be self-consistent. The time traveler might find that the closer they get to creating a paradox, the lower the probability of that outcome becomes. This creates a new kind of paradox at the intersection of the two theories. General relativity allows for the macroscopic geometry of time travel, but quantum mechanics seems to censor the consequences at the microscopic level. Which theory is in charge? Does the geometry of space-time dictate what is possible, or do the rules of quantum probability dictate what is allowed to happen within that geometry? The Novikov self-consistency principle is a classical GR idea that imposes determinism. The Deutsch many-world solution is a quantum idea that gets around the paradox by fundamentally changing the nature of reality. The quantum probability approach suggests a subtle interplay where GR provides the arena and QM sets the rules of the game to avoid contradictions. We do not know if CTCs can actually be formed in our universe. Most models require exotic matter with negative energy density, which may not exist. But the fact that our best theory of gravity allows for them in principle and our best theory of particles has to perform strange contortions to deal with the consequences is a deep paradox. It shows how the logical structure of time in GR clashes with the probabilistic and potentially branching structure of reality in QM. Number 4, the arrow of time. We experience time as having a clear direction. The past is fixed, the future is open. Coffee cools, eggs break, and people grow old. This directionality is described by the second law of thermodynamics, which states that the total entropy, a measure of disorder of a closed system, can only increase over time. This is the thermodynamic arrow of time. The paradox is that the fundamental laws of physics that govern individual particles do not have this arrow. The equations of general relativity and the main equations of quantum mechanics are time symmetric. They work just as well forwards in time as they do backwards. If you were to watch a video of two planets orbiting each other, or two electrons colliding, you could not tell if the video was being played forwards or in reverse. The physics would look perfectly valid in either direction. So, if the fundamental laws are time symmetric, where does the arrow of time come from? The standard answer is that it comes from the initial conditions of the universe. The universe started in an incredibly low entropy state at the Big Bang. It was extremely hot, dense, and smooth. This highly ordered initial state is the ultimate source of all the order we see around us. The universe has been moving towards a state of higher entropy ever since. Stars burn, life metabolizes, and everything slowly runs down. This just pushes the question back, why did the universe start in such a special low entropy state? This is a cosmological question that involves general relativity. The gravitational state of the early universe was very unusual. Gravity tends to clump things together, which is a state of high entropy. A smooth, uniform distribution of matter, like that in the early universe, is a state of very low gravitational entropy. So the paradox connects quantum mechanics through statistical mechanics and the definition of entropy with general relativity through the cosmological initial conditions. Why did the universe, governed by GR, begin in a state that was so thermodynamically improbable, allowing the second law, which governs quantum and classical systems, to create the arrow of time we experience? Some physicists, like Roger Penrose, argue that this requires a new law of physics. He proposes a Weyl curvature hypothesis, which postulates that the Big Bang singularity had a specific geometric property zero Weyl curvature that corresponds to this low entropy state. This would make the low entropy beginning a law of nature, not just a random fluke. Others look for solutions within quantum gravity. In some quantum cosmology models, our universe might be just one part of a much larger multiverse. Perhaps our Big Bang was not the ultimate beginning. It could be that the overall state of the multiverse is timeless or in thermal equilibrium maximum entropy, but quantum fluctuations can create baby universes that start in low entropy states and evolve from there. The arrow of time paradox is a clash between the time symmetric laws of the microscopic world, QM, and the time asymmetric evolution of the macroscopic world thermodynamics, which seems to be rooted in the specific initial conditions of the universe GR. We do not know why the universe was wound up at the beginning. Without that initial low entropy state, there would be no arrow of time, no complexity, and no life. It is a fundamental feature of our reality that our fundamental laws cannot, on their own, explain. Number 3, the landscape problem. For decades, physicists have been searching for a theory of everything that would unite general relativity and quantum mechanics. One of the leading candidates is string theory. In string theory, the fundamental particles we see are not points, but tiny vibrating strings. Different vibrations correspond to different particles. For the theory to work, it requires the existence of extra spatial dimensions beyond the 3 we know. These extra dimensions are thought to be curled up or compactified into tiny, complex shapes. The problem is that there is an enormous number of ways to compactify these extra dimensions. Each different shape of the extra dimensions leads to a different set of physical laws in our 4-dimensional world. The constants of nature, the types of particles that exist, the strength of the forces, all these depend on the geometry of the hidden dimensions. The number of possible geometries is staggering. A common estimate is 10 to the power of 500. Each one of these possibilities corresponds to a different, self-consistent version of the laws of physics, a different vacuum state. This huge collection of possible universes is called the string theory landscape. This leads to a profound paradox. If string theory is correct, why do we live in this particular universe with this specific set of physical laws? Why is the mass of the electron what it is? Why is the strength of gravity what it is? The theory does not seem to provide a unique prediction. Instead, it provides a near-infinite menu of possibilities, and we just happen to live in one of them. This is a failure of the traditional goal of physics, which is to explain why the world must be the way it is. The landscape problem suggests that the laws of nature might not be unique. They might be environmental, like the weather on a planet. This problem connects general relativity and quantum mechanics because string theory is a quantum theory of gravity. It is our best attempt to reconcile the two, but instead of a single, elegant solution, it gives us a messy, seemingly random outcome. One controversial way to deal with this is the anthropic principle. This argument states that we should not be surprised to find ourselves in a universe with laws that allow for our existence. In the vast landscape of 10 raised to the power of 500 possible universes, the vast majority would be sterile. They might have no atoms, or gravity might be too strong or too weak for stars to form. We, as observers, could only arise in one of the very rare universes where the physical constants are just right for complex life. To many physicists, this is a deeply unsatisfying explanation. It feels like giving up. It does not explain why the constants have their values, only that if they were different, we would not be here to ask the question. It turns physics into an environmental science, where we are just cataloging the features of our local patch of the multiverse. The landscape problem is a paradox of explanation. Our most promising attempt to unite quantum mechanics and gravity has led us not to a unique answer, but to an almost infinite number of them. Is there a hidden principle that selects our universe from the landscape, or is the existence of a vast multiverse the real answer, and the laws of our specific universe are just a random accident of cosmic geography? This is a fundamental challenge to what we expect from a final theory of physics. Number 2, the difficulty of quantizing gravity. The most direct way to try and combine general relativity and quantum mechanics is to quantize gravity. This means taking Einstein's classical theory and applying the standard rules of quantum mechanics to it. This is the same procedure that was successfully used to create quantum theories of the other forces of nature. For example, the quantum theory of electromagnetism, called quantum electrodynamics QED, was developed by treating the electromagnetic field as a quantum object. The result was a theory that describes photons as the quantum particles of the field. When you try to do the same thing for gravity, you run into disaster. The procedure seems simple at first. You assume that the gravitational field, which is the curvature of space-time, can also be thought of as a quantum field. The quantum particle associated with this field would be the graviton, a massless spin-2 particle that carries the force of gravity. The problem arises when you try to calculate the interactions between gravitons. In quantum field theory, interactions are calculated using a method involving Feynman diagrams, which represent all the possible ways particles can interact. When you calculate these interactions for gravity, the answers come out as infinities. In QED, infinities also appear in the calculations, but there, a mathematical procedure called renormalization can be used to handle them. You can absorb the infinities into a redefinition of a few physical quantities, like the mass and charge of the electron. Once you do that, the theory makes finite and incredibly precise predictions. Renormalization works for the strong and weak nuclear forces as well. But when you apply this procedure to gravity, it fails. Gravity is a different kind of force. The particle of gravity, the graviton, interacts with everything that has energy, including itself. This self-interaction is much more complex than in the other forces. When you try to renormalize the theory, you find that you need to introduce an infinite number of counter terms to cancel out an infinite number of infinities. A theory that requires an infinite number of parameters to make predictions is a theory that has no predictive power at all. It is non-renormalizable. This is a deep mathematical paradox. The standard successful method for creating quantum theories of forces simply does not work for the force described by general relativity. It is as if the two theories speak fundamentally different mathematical languages. This failure is what motivates the search for more radical approaches. It is why physicists developed string theory, where the point-like particles are replaced by strings, which smear out the interactions and get rid of the infinities. It is also why others developed loop quantum gravity, which takes a different approach by quantizing space and time itself, breaking them down into discrete, indivisible chunks. The difficulty of quantizing gravity is not just a technical issue, it is a sign of a deep conceptual conflict. General relativity is a theory about the background geometry of spacetime. Quantum field theory is a theory about the behavior of fields on that background. The paradox is that the gravitational field is the background. Trying to treat it as just another quantum field on a fixed background leads to mathematical nonsense. It is a hint that we need a new framework where spacetime is not a background at all, but an emergent property of a deeper quantum reality. Number 1, the problem of defining an observer. In both general relativity and quantum mechanics, the role of the observer is crucial, but it is defined in completely different and incompatible ways. This creates what may be the most fundamental paradox of all. In general relativity, an observer is a local, physical entity. An observer follows a path, a world line through space-time. They carry a clock and measuring rods. Their measurements of space and time are relative, depending on their motion and the local gravitational field. A key principle is that all observers are on an equal footing. The laws of physics are the same for everyone, regardless of their state of motion. There is no special privileged observer in the universe. In the standard Copenhagen interpretation of quantum mechanics, the observer plays a completely different role. The observer is a classical macroscopic system that exists outside the quantum system being measured. When this external observer makes a measurement, they cause the quantum wave function to collapse from a superposition of possibilities into a single definite reality. The theory draws a sharp line, the Heisenberg cut, between the quantum world being observed and the classical world of the observer. This is a paradox when you try to apply quantum mechanics to the entire universe. In cosmology, we want to describe the universe as a single quantum system. But if the universe is the system, where is the observer? There can be nothing outside the universe to observe it and collapse its wave function. Who or what played the role of the observer during the Big Bang? This is the central problem of quantum cosmology. If the entire universe is described by a single giant wave function, evolving according to the Schrödinger equation or its cosmological equivalent, the Wheeler-DeWitt equation, then it should always remain in a superposition of all possible states. It would be a superposition of a universe with galaxies and a universe without, a universe with life and a universe without. But this is not what we see. We see one definite classical universe. How did this single reality emerge from the quantum superposition of possibilities? The problem gets worse when you combine it with the ideas from general relativity. If an observer is just a local physical system within space-time, as GR suggests, then the observer themselves should be subject to the laws of quantum mechanics. They should have their own wave function and exist in a superposition, but if the observer is in a superposition, how can they make a definite measurement that collapses another system's wave function? This leads to a logical inconsistency. The quantum formalism requires a classical observer to make sense of measurements, but a complete theory of quantum gravity must be able to describe observers as quantum systems themselves living within a quantum spacetime. Different interpretations of quantum mechanics try to solve this in different ways. The many worlds view eliminates the need for collapse and an external observer by saying that all outcomes happen in different parallel universes. The decoherence theory explains how a quantum system, through interaction with its environment, can start to look classical, effectively hiding its quantum nature. But it does not fully solve the measurement problem. The observer paradox is the ultimate clash. General relativity offers a democratic view of observers within the universe. Quantum mechanics, in its standard form, requires a monarchical observer who stands outside the system and dictates reality by the act of measurement. A true theory of quantum gravity must explain how the democratic world of relativity emerges from the strange quantum substrate, and it must do so without appealing to a mythical external observer. It must explain how the universe can, in effect, observe itself.